Okay, so I hope you had a brief respite from the intense lecture series, and hopefully you're now caught up and well rested. So far we have defined the space of modular forms of weight k, and for the full modular group we've been studying those forms, and we found out that they were finite dimensional vector spaces, very beautiful formulas for their dimensions, and we also defined on this space these remarkable linear transformations, the Heck operators, that they seem to transform the space into that space, and somehow Ramanujan's conjectures were linked up with these eigenvalues of these Heck operators. That was the big breakthrough in terms of conceptual thought. Now, what I would like to do is pursue this vector space structure further by defining an inner product on that vector space so as to make it into a Hilbert space. So, this is Petersson. Petersson was a student of Heck, by the way, so this was his thesis. We'll define an inner product so as we can study the Hilbert space of Cuss forms. Okay, so let gamma be a congruence subgroup Can we turn these fans on also? I hope it's a little hot here. And I hope you can still hear me. Can you, let's let these fans start circulating. Maybe put it in 2. And let me know if you can't hear me. You can hear me? Okay. So for F and G, in the space of modular forms for this particular group gamma, we define the following. We define an inner product as follows. Okay, there's a problem with plus or minus I being elements in the group, so we saw that already earlier. So we're going to denote the group generated by plus or minus I and gamma, could be gamma. It'll be gamma if minus I is in gamma. So this we'll call this gamma bar. It's a small technical detail which we don't need to belabor too much about. Let script F be a fundamental domain for the action of gamma on the upper half plane. All right? Then we'll define F comma G to be the integral over this fundamental domain of y to the k f of z gz bar dx dy by y squared, and then we normalize it by dividing out by the index of gamma bar in SL2Z. So this is the definition of the inner product, and it's a small exercise to check that FG is linear, is bilinear, well, linear first in F, 2 that FG bar is the same as GF. 3 that FF is always positive unless F is identically 0. So this is a way, it's an interesting idea to metrize the space of modular forms. So we are going to measure the distance between two modular forms in this fashion. It turns out to be a very useful inner product. Now this is well defined. I'm going to leave these as exercises because this particular quantity y to the k f of z g of z bar is gamma invariant. As you can check, if f and g are modular forms, cusp forms of weight k for the group gamma, this is again gamma invariant. This measure is gamma invariant. Therefore, the whole thing is well defined. If I change the fundamental domain by another homeomorphic fundamental domain, it's just a change of variable with respect to the group SL2Z. Therefore, we will just get we will still get that this is well defined. So I will leave those small details for you to check perhaps in the tutorial. So let me just make one small theorem, though. That theorem which is going to be important for us to understand, and that is, suppose that gamma 1 is contained in gamma 2 are congruent subgroups. Then the point is that if you see, so for a modular form to be a cusp form on gamma 2 is the bigger group, okay? And therefore, we're asking for f of az plus b over cz plus d to satisfy that condition for more elements, okay? Therefore, sk of gamma 2, if f, so let me just make a remark here. Thus, sk of gamma 2 also satisfies these conditions, is contained in sk of gamma 1. So it's a kind of like a gamma, order reversing map. And therefore, if I have a modular form here, I can also consider it as a modular form here. And I've just finished defining the inner product. In some sense, I really should be putting a subscript gamma there because I did it with respect to this particular group gamma, but I don't want to do that. Just to clutter up the notation, I don't want to do that. So the point is now, if this is well defined, it doesn't really matter if you look at it as an element here or an element here. That's really the purpose of this normalization. So if f and g are elements in sk of gamma 2, then the inner product fg is independent of whether we view f and g as in sk of gamma 2 or fj as in elements of sk of gamma 1. Okay, so this is an important idea. And let me just give a quick proof and you can fill in the details. So proof. Let F2 be a fundamental domain for gamma 2 bar. Doesn't really matter. Take coset representatives. Alpha j such that gamma 2 bar is equal to alpha j gamma 1 bar. So it's these are finite indices, and therefore we will have a finite union. Let F1 then be these translates as before, and remember I mentioned to you that we can choose your alpha j's in such a way that this is a continuous connected domain, but that's not going to be relevant actually for the calculation. But the fact that the fundamental domain F1 looks like this will be relevant. So now calculate the inner product So this is the inner product of f and g viewed as elements of sk of gamma 1. And the point is that f1 can be written as a union of these. So you obviously write that. So you can rewrite this as this fudge factor times the summation over j of all that stuff, because I'm writing my fundamental domain F1 as a union of these things, therefore you end up getting this. Now you make a change of variable, and because the what are these alpha j's? Alpha j's are elements in gamma 2. Alpha j's are element in gamma 2 bar or gamma 2, and therefore when I make the change of variable, because I've started with a cusp form, f and g are cusp forms in sk of gamma 2, when I change variables here and remove this f2, make this alpha j inverse f2 into f2 itself by making the appropriate change of variables, you end up getting an invariant quantity. And it'll be the same for the number of copies. And how many copies are you going to get? Exactly the index of gamma 2 in gamma 1. And all you need to do is verify to complete the proof. Need only check that the indices match. So we need only check SL2Z gamma 1 bar. We need only check that this is equal to SL2Z gamma 2 bar. We need only to observe, not check. We need only note this so that I can replace this with the index of gamma 2 bar, and then I have this extra quantity, and that extra quantity is compensated by the number of coset representatives picking up the same quantity, and that cancels with the thing. So we need to only note that, and that completes the proof. All right. So this means that I don't have to worry about where the FG live. You could just take these inner products as they are. So with that technical issue out of the way, let us study the inner product and see what it has to say for our vector space. Okay, now what's interesting in this thing is that somehow, as I observed before, to understand the action of SL2Z, the full modular group, and the subgroups, somehow you had to go to larger things like GL2 plus R and so on and so forth. And so now, now we will have to do the same thing. So here's a small observation that will be relevant in the calculation. Suppose alpha is an element in GL2 plus Q. So that is a rational matrix, 2 by 2 matrix with rational entries with positive determinant. Suppose this is the case, and that alpha has integer entries. Let's suppose that. Let D be the determinant of alpha. If gamma is a congruent subgroup, if gamma of n is contained in gamma for some n, then gamma of nd is contained in alpha inverse gamma alpha, and it's also contained in the other way around. So this is actually a very elementary observation. I just want to put this in front of you because we will need it later on. Let's see why this is the case. To see this, note that for gamma in gamma of nd, we may write this element gamma. Remember, these are matrices which are congruent to the identity element modulo nd. Okay, so we may write gamma as the identity element plus nd times another matrix beta, say. Okay, so beta is a matrix. With integer entries. Then alpha gamma alpha inverse equals alpha of identity plus nd beta alpha inverse. So multiplying through with the distributive law, alpha times alpha inverse, this identity is still the identity, plus here now I can do the following. I can do that because these are just scalars. Yeah. So now the point is that this guy is equal to identity plus these are scalars, okay? N and D are scalars, ordinary numbers, so I can write this as n times alpha beta and push the scalar D into there. Okay, and now you know how to calculate the inverse of a 2 by 2 matrix, right? You know how to calculate it. It's alpha, beta, gamma, delta, and you just flip these things around, divide by the determinant, right? So if I have a matrix with integer entries, the inverse matrix is not going to necessarily have integer entries, but the denominator is controlled. The denominators will be the determinant of the matrix. Therefore, if I multiply by the determinant, this guy here has integer entries. So this guy's got integer entries. Beta has integer entries. And the point is that alpha has integer entries. That's my hypothesis here. Therefore, all of this stuff now has integer entries, and this parenthesis should be here. This has integer entries, right? Z entries. And therefore, when I multiply by n, it'll be 0 modulo n. I can talk about 0 modulo n. Therefore, this thing is now back inside. This thing is contained in gamma. Gamma of nd, sorry. Is that what I want? Gamma of n, sorry. Right? This thing is now in gamma of n. And because gamma of n is contained in gamma, you have that this is contained in gamma, and that's the rest of the proof. Is that okay? It finishes the proof. Yeah. Okay, good. Now, the other part I'm going to, is similar. You can do the other one. Okay, it's just completely equivalent. I think that when you try to put yourself back in time and see what Hecke was doing, I'm sure he was intrigued and enamored by this linear algebra that basically he had to review. And as you will see from today's lecture, it's just linear algebra, but focusing on this particular vector space. Very interesting theme. If I took alpha with rational entries, I might have trouble here with this step. I might have trouble here. See, this I could be able to probably control the other part, but I don't need it. It's a nice technical question. You can probably think about it, but I think it may not be true in general. Yeah. But for the moment, this is all I need, and you'll see it's just it's going to be an inner product calculation. All of a sudden, I need this little fact, and so this is all that I need, and that's good enough. So as a small exercise, let again alpha be in GL2 plus Q, have Z entries, show that there exists a gamma in SL2Z such that gamma inverse alpha has a triangular form. Has a triangular form for some positive, let's just put for some A, B, and D integers with A and D positive and 0 less than b less than d. So I'll leave that. This is just Euclidean algorithm, and maybe Karamdev can discuss it in the afternoon. Okay, so this small calculation that we need. Okay. Now, with these elements, alpha in GL2 plus Q, I'd like to see how the holomorphy is preserved under the slash operator with these particular elements. So, for example, we'd like to know, so let me just make a proposition. Let F be a modular form of weight k, gamma, for gamma a congruent subgroup, alpha in GL2 plus Q, then F slash alpha is holomorphic at every cusp. So let me try to prove this. So the point is that if I take an element alpha in GL2 plus Q, F slash alpha need not be a modular form of weight k again. Need not be. We have to know how the thing will transform. But the fact is F slash alpha still makes sense as a function on the extended upper half plane. I just like to check what's happening at the cusps. So what do we need to do? A typical cusp typical cusp S in Q is of the form S equals beta of I infinity. So we know that all the cusps are equivalent with respect to the full modular group. So there's a beta in SL2Z that will take I infinity to S. So to say that this is holomorphic at every cusp, remember I told you before when we were discussing behavior of the cusp, we did this trick of moving it to 0 by this exponential map. So we do the same thing now. So we need to check. So move it to infinity so that we can discuss it. We want to discuss this behavior, so we need to check. We must show F slash alpha slash beta is holomorphic at I infinity. To say that I want to show F slash alpha is holomorphic at S is equivalent to saying F slash alpha slash beta is holomorphic at infinity. Because when I plug in infinity, takes it to S and that's holomorphic, right? Yeah. So, but that's equal, but this guy, the slash notation was so nice that when I do this, that's just F slash alpha beta. And you know that the action of the thing is that such that if we multiply by a scalar matrix, nothing happens to the action of the function. So I can always multiply alpha beta by a scalar without affecting the this function F slash alpha beta. And what we do is, so we may suppose that alpha beta now has integer entries, because alpha, remember, was an element here, and it's just a 2 by 2 matrix. There's some fixed denominators, okay? And so we can multiply by a scalar to kill those denominators. We still have that. So without loss of generality, we may suppose beta is already in SL2Z, so that's got integer entries. We may suppose alpha beta has integer entries. Since we can multiply alpha beta by a scalar matrix, and that doesn't do anything. By scalar, not a scalar matrix, a scalar, because you want to kill the denominators, right? A scalar without changing f slash alpha beta. Right. So we do that. Now by this elementary exercise, you give me any alpha now, I can find a gamma in SL2Z such that this happens. So by the exercise, we can write. So I'm going to apply the exercise not to alpha beta. We're going to apply it to this guy. So we can write alpha beta as equal to gamma applied to A, B, 0, D with gamma in SL2Z. So what is the point of doing that? If I can do that, then I'm trying to study f slash alpha beta. So then f slash alpha beta turns out to be f slash gamma A, B, 0, D. But f slash gamma, this is f slash gamma slash A, B, 0, D. Keeping in mind that gamma is in SL2Z. Okay, if gamma is in SL2Z, f slash gamma is now holomorphic. F slash gamma is not going to be gamma because gamma in it, f is a modular form of weight k for gamma, and gamma is not necessarily SL2Z. But what we want to say is that f slash gamma is holomorphic at infinity, at every cusp. F slash gamma is holomorphic at every cusp, and therefore this change of variable, this is just AZ plus B over C over D, so which is holomorphic at infinity. I believe this is really the part motivation for the definition of cusp form. You want it to vanish everywhere, you want it to be analytic at every cusp, not just some of the cusps and other cusps. That's why people don't study that. And I suppose the theory of mock modular forms is kind of like trying to move the theory of modular forms in that direction, where you now relax these conditions or relax the conditions of holomorphy at some of these cusps and try and build a bigger theory. But this is not the place for mock modular forms, but I just thought I'd mention that fact. Pardon me?
In the last line,
Yeah.
F is holomorphic at every cusp. We have given F is holomorphic at every
F is holomorphic because F is a modular form of.
F slash gamma is holomorphic at every.
Right. Yeah, because F is holomorphic. Oh, that's what you're trying to say. Oh, yeah. F slash gamma is holomorphic at every cusp, since F is holomorphic at every cusp. That's right. Okay, so that proves that when I take an element in GL2 plus Q and I look at this F slash alpha, F slash alpha is again holomorphic at every cusp. Good. Moreover, I mean, here, of course, you can actually calculate what the Fourier expansion is. If you had the Fourier expansion of f of z, you know how to calculate these Fourier, because this is a very explicit transformation. It's just az plus b over d. So you can write down the Q expansion of that thing. So it's now difficult now to see the following exercise, which I will leave you to do after this calculation. If f is actually a cusp form, that is, it vanishes at all the cusps, gamma is a congruent subgroup of SL2Z, alpha is again GL2 plus Q, then f slash alpha vanishes also at every cusp. And that you should be able to see by Fourier expansions, because this is again an explicit change of variable. Okay. With these technical aspects in place, let me now try to prove the following theorem. Let gamma be a congruent subgroup of SL2Z. Let alpha be in GL2 plus Q. And suppose that alpha has integer entries. Put gamma prime to be alpha inverse gamma alpha intersect gamma. Then gamma prime is also a congruent subgroup. And the map f goes to f slash alpha takes mk of gamma to mk of gamma prime, and sk of gamma to sk of gamma prime. So this is what I'd like to show. So we've already checked that this slashing respects the behavior of the function at the cusps. We've already checked that. We need to check the modularity relations. Now that I've got this new thing, the modularity proof, let D be the determinant of alpha. Then by what we already saw in one of the earlier observations, we already have this fact to us. And gamma ND, is also contained in, since gamma, let's see, how does this work? Yeah, so well, this is already, this is contained in SL2Z. No, sorry, this is not contained in SL2Z. So what I want to do is I want to take the intersection. So this is from the previous calculation. I want to say this, which is now contained in SL2Z. So the point is that this guy contains gamma ND, therefore, where is it? Here it is. Therefore, gamma prime is a congruence subgroup of that. Okay. is a congruent subgroup. All right. So if tau is an element of gamma prime, we can therefore write, keeping in mind that gamma prime is of this shape, we can write tau as alpha inverse gamma alpha for some gamma in capital Gamma. Hence, see, what do I want to show? I want to show that we've checked the behavior of the function as a holomorphic function, that it's okay, but we need to check the modularity. So I need to check f slash alpha slash gamma, where gamma is an element in gamma prime. I need to check what happens. So take an element tau. Oh, so I should have said tau. F slash tau. I need to check that f slash tau is f, with tau being in gamma prime. I take the element tau and write it as alpha inverse gamma alpha with gamma in little gamma in capital Gamma. Then f slash alpha slash tau is the same as f slash alpha times alpha inverse gamma alpha. And because of the nice property of the slash operator, this is just simply this. But then that's equal to f slash gamma slash alpha. But the nice thing is f is an mk of gamma. Therefore, f slash gamma is gamma. So that's why I use this gamma here. So this is just f slash alpha. So that means when I slash with tau, I get back this. Therefore, f slash alpha is in mk of gamma prime. So by taking this element alpha and slashing, I get a mapping from this particular vector space mk of gamma into this other vector space. And the same, now I have to check the cusp form business, but I'm going to leave that to you to do, because what does it mean to say it's a cusp form? Well, if it vanished at those cusps, I have to check what is it doing at the cusps for here. Well, in those cases, you have an explicit calculation again of the Fourier expansion, and therefore it's not a difficult thing to check. So similarly for sk of gamma. All right. Okay, so now I'm going to move a little faster because I'm going to get stuck if I keep on doing this. So let gamma prime be a subgroup of GL2 plus R if f prime is a fundamental domain for gamma prime and alpha is in GL2 plus R, then alpha inverse f prime is a fundamental domain for the action Okay, so this shouldn't come as a surprise. You could just check that's the case. So I'm going to leave that also as an exercise. Okay, now we're all set to prove the fundamental theorem that's going to allow us to show we have a nice inner product. A Hermitian with respect to Heck operators, Hermitian with respect to Heck. So if f and g are in Sk of gamma, again, gamma is always a congruent subgroup. We're not dealing with anything else here. And alpha is in GL2 plus of Q, then the inner product of F and G is the same as the inner product of F slash alpha, G slash alpha, where the latter inner product is the inner product on the space of with respect to gamma prime. So is the inner product see, I told you that when I defined the inner product, I was defining it with respect to a particular group. The point is F and G were in Sk of gamma, then this is an inner product with that particular group. F slash alpha and G slash alpha are actually in that map that I gave you on the previous theorem that I wrote down here. F slash alpha sends elements of Mk of gamma to Mk of gamma prime, and therefore this is really speaking an inner product on gamma prime. But then I went through all that trouble at the beginning to show you that it doesn't really matter what, you know, it's independent of that thing the way you view it, so we just drop these things. Okay, so this shouldn't come as a surprise. What you do is you use this fact to calculate the inner product, make your change of variables, and do the natural standard thing. So this is not a surprise. All the stuff that has been done earlier leads to this. Okay, so this shouldn't come as a surprise. Now, with this in place, we're ready to prove the basic theorem. I just want to give you one more tiny exercise, which is actually very easy. And I'll tell it to you orally how to do it. Exercise. Let alpha be in GL2 plus Q, have integer entries. Let with determinant D, let alpha prime be equal to D times alpha inverse. For F and G cusp forms, okay, K and gamma, we have F slash alpha G in the right spaces is equal to F G slash alpha prime, where alpha prime is this element. And the solution or the proof requires you to use this, replace G with G slash alpha inverse in the previous, in the theorem. If you you have to do a little bit of checking, but if you do that, you will get the result. Okay. All the technical stuff is now out of the way. I want to show that these Hecke operators have some remarkable properties with respect to this inner product. First thing, our goal is twofold. We want to show that these Hecke operators have the property that they're Hermitian operators on the space with respect to this inner product. Okay? So you all know from basic linear algebra that once you have a Hermitian operator on a vector space, the eigenvalues are real. This is something that and you can do wonderful things about diagonalization and other things too. So that's what we're want to show this. This is the first thing. Second thing is we want to show that the TNs are actually commuting operators. We want to show that the algebra of these Hecke operators is actually a commutative algebra. And the point is that if you have a Hermitian operator on a vector space, you know that there's an orthogonal basis with respect to that particular operator. But if you have a family of commuting operators, you can simultaneously diagonalize the vector space so that you have a basis for every single operator. Okay, so that's the punchline for the second. The second part means that not only is it Hermitian with respect to a single Hecke operator, it's Hermitian with respect to the whole algebra. Not only that, but you have this commutative algebra of operators. So when you have a commutative algebra of Hermitian operators, you can diagonalize the vector space to have a simultaneous diagonalization. So it means an orthogonal basis with respect to all the operators. So that's the goal. So hopefully I'll finish this in the next half hour. So let's begin with the commutativity. And the commutativity is very easy if you remember how the Fourier expansion worked. So what is Tn of f do? If I have f and its Fourier expansion, what does Tn of f do to the Fourier series? And what is Tm of f? What does Tm do to? So basically, we need to study Tn of Tm of f and Tm of Tn of f. We need to study these two objects. So we already knew that if I have, now this is essentially elementary number theory. So to do this, let's first do the case 1. M and n are relatively prime. In this case, we have actually Tn, Tm, turns out to be Tmn. So we'll show this. We'll show that when you take the product of these two, it's just T sub that product. And once you do that, then you see that Tm times Tn is the same thing, therefore you get the equality. So let f be a modular form. Again, for the full modular group. And let's write f of z as summation r going from 0 to infinity, lambda of r q to the r. Then we already showed, we computed that Tn of f has Fourier expansion b of r q to the r, where b of r is equal to d divides n and r, the GCD of n and r, d to the k minus 1, lambda of nr over d squared. So we already did this calculation of how the Fourier coefficients change under the Hecke operator. So we have this very clean formula. Let's write Tm of f So let's write the Fourier expansion of Tm of Tn of f in terms of the C's. And if I know the Fourier expansions, Fourier coefficients of this guy, I know how to calculate this from the same kind of formula. Then C of r is equal to E divides the GCD of m and r, e to the k minus 1, times b of m times r divided by e squared. So there's a then. We have this formula. C of r is this thing. But I have this formula for b of r. D divides the GCD of n and mr over e squared. Okay? Now the point, this is where I'm going to use m and n are relatively prime. The point that m and n are relatively prime means that here I have e dividing m, okay? E dividing m, and this m over e can be eliminated. So let me try and say that properly. So here we have essentially e dividing m and r, e to the k minus 1, d dividing the GCD of n and r over e. The point is, n and m are relatively prime. So here, mr over e squared, I'm going to write as m over e times r over e. Okay, e divides both m and r. Okay, so these are all integers. M over e is a divisor of m, and m and n are relatively prime, therefore I can get rid of it. That's how I got rid of it. So that's d to the k minus 1 times lambda of m and r over d squared e squared. Now, because n and e are relatively prime, remember that e is a divisor of m, and n and e are relatively prime, I have the following fact. I can, because n and e are relatively prime, I can actually eliminate this r over e business and change it to r. Okay, so e is a divisor of m. Okay, so what has happened here is whatever divisors of r that have been removed by e, I don't need to worry about this. So this actually, so observe that the GCD of n and r over e is the same as the GCD of n and r over e times e, because e is a divisor of m. M has nothing to do with n. Therefore, if I tack on this guy, nothing happens. Everybody okay with me? So this is the same as the GCD of n and r. That's how I did this. I'm going to remove this now. Now, the point is that as E runs over the divisors of m and r, and D runs over the divisors of n and r, because m and n are relatively prime, dE is going to run over the GCD of Mn and R. This is just basically elementary number theory, but of course you have to know what you're doing. So this is equal to E divides, so I can combine both of these things and say that this is simply a sum over T dividing the GCD of Mn and R. See, the point is that M and N are relatively prime. E dividing M and R, the GCD of M and R, and D dividing the GCD of N and R is the same as saying dE, which is I'm calling T, is going to be the GCD of Mn and R. So if I started with a modular form with the Fourier expansion here, given by the lambdas, well, that's the coefficient for Tmn of f. The coefficient, Fourier coefficient of Tmn. Therefore, I've shown that Tn times Tm is equal to Tmn when M and N are relatively prime, and then of course you can flip it around and you get the commutativity there. So for the prime powers, it's a little tricky, and I'll just show you how that's done and see if you know, and leave some of the details for you to work out in the afternoon, and in case students are stuck. For prime powers, we need a subtler argument. We need to show if P is prime, Tp to the S, Tp is equal to Tp to the S plus 1 plus P to the K minus 1 Tp to the S minus 1. Okay, now if you don't mind, I'm going to relegate this to the afternoon tutorial. What you need to do is, it's all done very neatly and cleanly. What you need to do is to introduce a slash notation. So looking at the Heck operators as in terms of a slash notation, and it's just matrix manipulation of those coset representatives. So I'm going to leave that fact to you to do. It takes maybe about 15 minutes or so. And the advantage, once you have this particular recursion leads to this recursion. You will remember, by the way, this looks very similar to Ramanujan's second conjecture. Like tau p to the s plus 1 is equal to tau. It's exactly that. It's more or less that. But of course, you're now dealing with these linear transformations as linear transformations. This identity actually holds. So what you need to do is you need to show that, firstly, Tp to the s is a polynomial. P sub s is a polynomial with integer coefficients. So for powers of Tp to the s is actually a polynomial in Tp. That's exercise number 1. And exercise number 2 is to show that Tp to the s times Tp to the r is the same as Tp to the r times Tp to the s. So that basically, using this, you are able to now confine your attention to prime powers. For a fixed prime power, you would then use this fact to show this. So these are, this is not an easy exercise, but it's a longish exercise, but it's pretty routine. It's just matrix manipulation. So I'm going to leave that, and with these two in place, you can then happily extend this fact that using this, you can show that the algebra of TMs is a commutative algebra. I'm not saying that this is true for all M and N. I'm not saying that. What I'm saying is what we have is TN, TM is the same as TM, TN for all M and N. So those two different statements, right? In fact, it's not true that you have this property when M and N are not relative prime. But you have this. So this is a commutative algebra operators. So that's the key point. Okay. Now I think we're ready to prove Peterson's theorem. For any n bigger than or equal to 1, Tn of f, inner product with G, is the same as f, inner product with Tn of G. Proof. Well, by what we just calculated, we showed that the Hecke algebra is generated by Tp to the alphas, or Tp to the s's. But each Tp to the s is a polynomial in Tp. And therefore, the Tp's generate the entire Hecke algebra. It suffices to show, a little bit of reflection shows, it suffices to show that Tp of f, G, F Tp of G, because every Hecke operator is polynomial in this, and there's a linearity of the inner product. So you multiply these things together, and then you have this is all that suffices. Once you show this, you can deduce the general result for all primes P. So for primes P. Okay. But Tp of f can be thought of as p to the k over 2 minus 1 f slash p001 plus b running from 0 to p minus 1 f slash 1b0p. Keep in mind those representatives for the action of the Hecke operator, right? So this is basically, using the slash notation, I can write neatly Tp of f in this fashion. Okay. So now, by our earlier work, thus, by linearity, the inner product of Tp of f with G then is just simply equal to p to the k over 2 minus 1, the inner product f slash p001 with G plus summation b going from 0 to p minus 1 f slash 1b0p comma G. And now you know why I had to belabor dealing with all those alphas with rational entries and so on and so forth, because these matrices, of course, are not in SL2Z or anything like that, but they are in GL2 plus Q. And I'm looking at these F slash that with alpha and GL2 plus Q. Therefore, I need to know the behavior of this thing, and I need to know their behavior with respect to the inner product. That's why I went to all that trouble. Now you can see what to do. So by our earlier work, by our earlier remarks, F slash P001 comma G is equal to F G slash 100P. Remember that inverse, that matrix, right? Yeah. And then you get rid of it by multiplying by the determinant. And so this means that since F slash alpha comma G is equal to F G slash alpha prime in our earlier, where alpha prime was equal to D times alpha inverse, where D is the determinant of alpha. So I can replace this guy with this guy. What about these guys? Well, for each of those, I do F slash 1B0P comma G by using the same result. I see that this is equal to F. Okay, so this is not totally trivial. So let me do this carefully. Yeah, let me do this carefully. Sorry, I don't want to do this too rushed. So for each one between B and P minus 1, let alpha be equal to 0, minus 1, 1B. So keep in mind that this is an element in SL2Z. And beta is also similar, but not quite with this, minus B. Then F slash 1, I don't want to cram all this. Let me just kind of move here so that you can see it better. So I finished analyzing this guy. I just told you how to do that. Now I have to do this one. So F slash 1B01 comma G is equal to F comma G slash P minus B01 by that earlier remark, okay, with that D alpha prime that I wrote down. Now, as F is a modular form for the full modular group, F slash beta is equal to F, and G slash alpha is also equal to G, because these are modular forms for the full modular group. And alpha and beta are in the full modular group. Okay. So I'm going to replace G here with G times alpha. Then, thus, F comma G slash P minus B01, this inner product is equal to, well, I'll just put F slash beta because F slash beta is the same as F, and then G slash alpha P minus B01. No, gamma is SL2Z. So this is a full modular group. So this is gamma of 1. I should have put SL2Z. So we're not doing subgroups at the moment. We're doing the full modular group. Yeah. In fact, this is a serious problem. How to extend this theory to higher, other congruent subgroups was a big thing that stymied Hecke for a long time, and it wasn't solved by him. It was solved by Atkin later. So we'll come to that later. Yeah. Yeah, it's a full modular group. So we're still at that. So this is okay. And now Okay, let me just backtrack here. So let's change this thing here. So remember the theorem that I had, which said f comma g is equal to f slash alpha g slash alpha. Okay, so you got that. So I'm going to slash both of these things with beta. So this is equal to f slash beta g slash p minus b 0 1 beta. Okay, that's goes back to our earlier theorem. But now I'm going to change g to g slash alpha. Because g slash alpha is g. And now, when you check what this matrix is, see, alpha is explicit, beta is explicit. You just do the matrix multiplication. Lo and behold, this comes out to be f slash beta is f comma g 1 b 0 1. In other words, I managed to move this matrix to the other side. And that's it. So then now you're able to add these things through, and by linearity you get the result. So now you get this. So almost finished. Yeah, so this gives us now a family of Hermitian operators. So from linear algebra, all eigenvalues of T sub n's are real. If you have a Hermitian inner product, if you have a linear operator which is Hermitian with respect to this inner product, then all the eigenvalues of the Hermitian operator are real. That's a general theorem. So that's point number one. Point number two is, moreover, the eigenvalues are algebraic numbers. Now this is a very important thing, so I don't want to rush this. The eigenvalues are, once we normalize it, of course, I normalize it, are algebraic numbers. Provided we normalize our Fourier expansion so that the lead coefficient is 1. So we normalize. I mean, if you take an eigenfunction, any scalar multiple is still going to be an eigenfunction, so it's not going to be any. So you can't really, you can change the, you have to fix something, normalize it, so that the lead coefficient is 1. The key idea here, and this is where I'm going to use level 1 structure. The level 1 structure tells me that the space of modular forms of SL2Z is a polynomial, is spanned by these Eisenstein series. By these things, E4 to the alpha, E6 to the beta, with 4 alpha plus 6 beta equals k, right? This is that. And E4 and E6 have integer coefficients, so everything's got integer coefficients. So we got a basis with integer coefficients here. And therefore, since I have a basis of modular forms with integer coefficients, you know what we mean by go back to your linear algebra and review. If I have a linear transformation on a vector space, and I would like to give a matrix representation of that linear transformation, what do? You take a basis, and you see what the linear transformation is doing on that basis, and then you write that element as a linear combination of your basis elements, right? So if I have the Hecke operator Tn, it's a linear transformation on this vector space. Right? And so I have this very nice basis of integer coefficients. So if I now try to write what is Tn of E4 to the alpha, E6 to the beta as a linear combination of those things, you can see it's just going to be rational numbers. Okay, so the matrix representing Tn is a matrix with rational coefficients. Eigenvalues of that particular matrix are the eigenvalues of the Hecke operator. Therefore, they're algebraic numbers. That's the key. The key is it's spanned by these things, but these things have z coefficients. And therefore, the matrix representing the Hecke operator is going to have rational coefficients. Because you're going to invert a matrix, so you may have some, division by some things. So that's a very important idea. The other idea that I forgot to mention maybe about 3 or 4 lectures ago is that the same basis allows you to take a modular form with algebraic coefficients right? You have a modular form with algebraic coefficients, so an is now in Q bar. Then what I'd like to do is I'd like to apply a Galois automorphism to each of the coefficients and not to anything. This is the definition. F sigma of z I'm going to define to be an sigma e to the 2 pi n z. So the theorem is that if f is a modular form of weight k on gamma, then so is, for gamma of 1, this is rational structure, then so is F sigma. That's not a trivial fact, that you can apply Galois to the coefficients and still get a modular form. There you're using the fact that you have some sort of what's called rational structure for the space. That is, the basis has z coefficients. So this is an important consequence of the same idea. I just wanted to highlight that. Okay, now I have more or less run out of time, but let's just see what I have to say. If you don't mind, I'll take 5 minutes. Is that okay? There's no class here, right? Okay, yeah, just check. Otherwise, you'll have to do a little bit. There is a class. Okay. Okay. So let me just say in one sentence. Then we have this vector space Sk of gamma of 1, and we have now a commutative family of Hecke operators. For all n in natural numbers, we have this family of operators. And so the point is, with all that work that we just finished doing, that it's a commutative family, it's acting on this vector space, and a beautiful theorem of linear algebra says if you have a commutative family of linear operators acting on a vector space, you can simultaneously diagonalize the space. So therefore, there exists a basis of eigenforms of the Hecke operator. So all of these spaces have nice basis elements, and these are going to be eigenfunctions of the Hecke operators, and they will have Fourier coefficients which are algebraic numbers because of this property. And that is an important idea. I do the linear algebra in the book if you want to check it, but that's basically the last piece of things that I wanted to tell you. And Hecke and Petersson tried very hard to generalize this to higher levels. That's where the problem begins. So that's what's called Atkin-Lehner theory. It wasn't done, they weren't able to do it. So that's because you don't have a theorem which is so neat and clean with respect to these. Firstly, we used SL2Z quite a bit. So there's a lot of things that have to be tidied up. And the other thing is, of course, the nice explicit basis that you have for the space of modular forms. Okay, so I'll stop.